Okay, it's almost 12:05. Let's make a start. Welcome to this iStructy London Young Members Group's technical talk on how Python can help with everyday structural engineering. Before introducing today's speaker, I will quickly run through some housekeeping notes. If you would like to ask a question, please drop it in the chat and we'll address it towards the end of the event in the Q&A session. If you encounter any technical issues, please try to refresh your browser. And the final one, this is a recorded event and the recording will be available in the next few weeks on the iStructy's YouTube channel. This leads me on to introducing today's speaker. We are pleased to have Timo Harbo, a founder of Timo Harbo APS, with us today. Timo is a leading expert in computational design with a background in structural engineering. He's worked on many landmark projects worldwide and led computational design strategies at Birke and Rumble. With his passion towards integrating engineering, design and coding, Timo aims to optimize project processes and empower engineers to focus on innovative design. Today, Timo will share his expertise on how Python can help with everyday structural engineering, from processing FEI results, creating calculation templates, to generating informative plots. Timo, welcome. It's a pleasure to have you with us today. I will hand it over to you.
Thank you so much. And it's really awesome to see that many people in this call here. So thanks a lot for joining, everyone. I just quickly want to say kind of my intention with this presentation here. A lot of people, when you hear Python or learn Python, it's very much about this. Now you need to be a programmer. But I kind of want to show with this presentation how Python can be a tool to do better engineering. So it's very much kind of like a pragmatic approach to programming. You don't need to know everything about programming to make your engineering work better and faster. So that's what I'm going to focus on in this presentation here. So that's also why the title is about everyday engineering. It's not about building big grand tools. It's about solving your engineering tasks in a better and more efficient way. Before I get that far, I'll just share my screen here and maybe give a little bit of background. Now, you already were told a little bit, but just to give you an idea of where I come from. So I am a structural engineer. I started in Bjarke Ingels Group in the engineering department, moved on to the high-rise department in Ramboll, and now I'm running my own little consultancy, very much focused on automation and computational design and programming. So some of the projects that I've had the pleasure of working on are these here, and I picked out these here because I've also used a lot of Python on all these projects here for all sorts of different tasks, from out of necessity, because in some cases we had so much data, and other times, especially when I was learning, also just to try a new way of solving some tasks. So the agenda for the presentation here is first, why Python? Well, I just quickly want to tell you why I think Python is a great skill set to have as a structural engineer. Then we're going to touch on something called notebooks and give you an introduction to what those are. And then I'm going to come with lots of examples in all directions. So if we start with why Python, I think most structural engineers have been through a lot of Excel templates. And I just want to show you an example of the exact same code written in an Excel template and written in a Python script. So you can see here I have a function in Python called beam with point load deflection. And you can kind of read what's going on here. At least when you've learned some basic Python, then you can see what's going on here. But the same functionality in Excel often looks like this here. With that being said, Excel is something like, it's an amazing tool. You have to use it and we cannot get around it. But I think there is a space for Excel to do one thing and Python to do other things. So some of the key arguments that I think Python is amazing is that it's very easy to read. It's easy to QA. So as you saw with the formulas before, it's very easy to see is an error in a formula somewhere, which can sometimes be harder in, for example, Excel. The syntax is a lot simpler than other programming languages. It's easier to get into, it's easier to learn. It integrates quite nicely with Excel. I know that Microsoft is also working on actually being able to use Python directly in Excel, but you can load Excel files into Python, you can you can write Excel files out. So there's a good integration with existing tools and data. Then you can kind of break it down into small little modules. So you can reuse your code, so you don't have to do the same thing over and over. There are lots of external libraries, so you can kind of rely on the work done by others in very well-maintained and QA'd libraries. And now with ChatGPT and other AI tools emerging really, really fast, it is so much easier to learn because you basically can use AI as an assistant in your learning and in your writing. I think in the last 2 years, I've sped up the speed with which I write Python by factor 5 or something. So it's really, really, it's a new time to be learning programming in. So if you haven't used Python before, just give a quick introduction to how you actually use Python. It used to be that Python was something like you wrote one long file or several files with code, some comments in your code, and then you could run this code file. Not very beginner friendly, but it worked very well. But it's very much this like it's a programmer's task to write these. But then notebooks came out, and I'll just show you an example of a notebook here if I can get it to work. I have it here. So a notebook, if I can run in your browser like this here, you can write it as a Word document. So I can say, here is an explanation. And then I can add some code down here. A equals 5, B of V equals this. And you can say A plus V. And then just needs to load now because it's starting up. But then you can run the code. And this here is a notebook. So you can see how you can use these here to create templates for calculations with explanations and images and everything. So just to show you an example, let's see if I can get that over here. This one here is from a course I'm developing, one of the lecture notes here. Where you can see as you go down, you have figures presenting the problem you're working on. You can write mathematical formulas out very nicely. And you have all the code, and you can basically just go up and say, run the code. And then it goes through all the code for you. So it's a very friendly way to work with code rather than just having one long file of code, which is what you often have if you learn other programming languages. So notebooks are awesome, and they can often run in your browser. Then I'd say they can run in your browser. There's often that you want to share a tool where you can just maybe upload an Excel file and you can do it all. For example, in this platform I just showed you here. Other times you want to run them on your desktop, so not online, and that's also perfectly possible. So you can run them in your browser, on your computer, however you want, and it's the same thing essentially. So that was notebooks. See it as Word documents with code in them where you can generate figures and everything. So let me show you some examples. And one of the first examples I want to show you is text file editing. So let me show you a file. If you have worked with finite element models and generating file element models, oh, I need this one here. Then you have also seen some of these input files that you can sometimes have. Oh, I'm just catching it over on the other screen here. Sorry about that. It was here. Yes, please open it. There we go. So you have these text files that you use to define an FE model, and they can look like this. This is from ETABS. So your entire model is defined by this file here. You can see you have all your rebond definition, your point locations, and the whole model is a big text file. And this is extremely useful because at least what I've had to do quite often is, for example, for the springs under a building, then I send some reactions to the geotechnical engineers. They come back to me and they want to have their pile stiffnesses updated. So there I would like to be able to just put their numbers in automatically. That could be one use case. Another use case could be that I want to check the sensitivity of my soil stiffness. So maybe I want to see what if our soil stiffness is just like plus minus 20%. How does that affect the building behavior? So what you can do is you can write a Python script that reads through this file here and looks for, let's show an example here. This is the Python script. This is not as clean as some of the other ones. This is a bit of a like sandbox file, I would say. Let's quickly go through it here. I make a folder on my computer where I say I want my output files here. I find my base model, this file I just showed you. I'm not going to go through all of this, but down here, what I then say is that I want to look for this piece of text in my file, and I want to replace it with this here. This is an extremely simple example. You can make them more complex, but just to show you the idea of it. And then you can run the code and it will generate a new file for you. So I've made another example down here where I say, I want these stiffnesses to be in my springs. And just to show you the files that come out of it. Sorry about that. I just had it open in text file editing. There we go. So then what it spits out is 10 new files. And then you can also use Python to automatically actually run ETABS, to run all these models for you. So essentially you could have one model. You can say, hey, I need to update my spring stiffnesses, rerun the model, and actually show me the results immediately. So you can take it to all levels of automation. I personally like to have this very, very simple workflow where I just update a text file because it's simple, it's easy to see what has been changed, and it's not a scary black box. So each of these files here represent an FE model with changed values. So I think this here is one use case that I've used a lot. And it's simple to learn. You can get ChatGPT to also write a lot of it for you. So really, really useful low-hanging fruit. Then another example or something I use it for is for plotting, like creating visuals, creating plots. So often we have, in all the jobs I've had, we've had a lot of Excel templates where you could kind of copy paste data in from one place, and then you could generate these nice plots in Excel. But there, Python is, in my opinion, really superior. So this here, it's again a file from my courses, as you can see here, but I go to the bottom to show you the plot. So when you work with design of floor slabs and footfall vibration, this is a plot you've most likely seen before. And it's one that actually, like, it takes a bit of effort to create a plot like this in Excel. And I had to do it before because I wanted to show to the client that, hey, we have a requirement in our office for a response factor laying at this level here. But then I also want to communicate where our data point we're laying on this plot. And maybe even that one point here is above the requirement, but we're okay with that because it's outside seating areas, for example. Plots like this are really quite simple to generate with Python. And I'll actually just go through this notebook to show you how it's done. Not in a super detailed way, But to give you an idea, so you start by importing different packages you will need. So these are these external libraries I mentioned in the beginning, pandas being the Excel equivalent in Python. So you import these. Then you have a mathematical formula. This is from the CCIP 016, like the Concrete Center in the UK, their guide for vibration. They give these three formulas for the base acceleration curve, essentially. So we can turn this one here into a function. So this here is exactly equivalent to this little piece of Python code. And if you read it line by line, I think it's actually quite simple to read. If I zoom in a little bit, it's basically just like, if the frequency is less than 4, then use this. If it's less than 8, then use this. Otherwise, use this. So it's very intuitive translation from math to code. Then we generate a lot of frequencies. You can see we check all these different frequencies, and for every frequency, we calculate the baseline acceleration. And then we go down, and first we create a plot, like the simplest plot possible of this, essentially. We say create a plot the frequencies on X, the baseline acceleration on Y, and give the plot a title and some labels for the Y axis and for the X axis. And then we get this plot here, which is obviously lacking some information. But then with Python, we can go in and we can change the logarithm to a logarithmic scale. We can put some grid lines in. And the funny thing is, if you take this code up here, copy it in to ChatGPT and say, hey, I would actually like to have these grid lines, like a legend, all those things, it can help you generate most of that. So we go through the next step, get the grid lines in. And lastly, we can import our data from our model. This is just written in text, but you could import it from an Excel file, for example. So we want to show an acceleration for this frequency, another acceleration for this frequency, and another acceleration from this frequency, and add some text to the plot. And then you get a pretty nice plot here. And of course, you don't want to do all this coding every time you have to make a plot. I would say this is one of those plots. You make this template once, and then you give the input parameters to the person using it, so you can change it to be residential limit. You can change the response factor. And then you just have this template in your department, and you always have a nice visual to put in to your documents that you send to the client or other stakeholders. So that's for plotting, and you can make any type of plot you can, I think, ever imagine. The next example here is one that I've been quite excited about showing, because I was preparing this presentation here the other evening, and I was thinking, okay, I want to really show how I use ChatGPT in my whole process, and it is a skill to learn how to do it in a good way. But let me show you how I did it here. So I had this file here from my FE software. So you may have different ones for the software that you're using, but I think this is quite similar to other programs. So in this tab here in this sheet, you see we have the names of our nodes. We have some X and Y coordinates. In here, I have a long list of my reactions in the nodes in the model for every load combination and type of load combination. So if I was to write an Excel template to create a reaction plot using this data, I would probably make an Excel template where I would copy in the unique name over here. I would copy in this, the vertical reaction. Then I would do a VLOOKUP into the coordinates and have another column here with the coordinates. And then I would maybe do a pivot chart or something. And then I would take one load combination, save the image out, take another load combination, save the image out. And that's a perfectly valid way to do it. But I wanted to try something with ChatGPT to see how fast I could actually do it using ChatGPT. So I uploaded this Excel file without doing anything to it, just raw as it came out of ETABS. And then I was quite specific in my prompt here. I said, okay, I have 3 sheets. There's one that has the location, others have all the things you need. And I give it some hints to what I think it needs to do, because I know what needs to be done with this file if I was to program it myself. So I tell it very explicitly what I expect it to do. And I say that I want a plot with the X and Y location, and I want the color in this plot to show the vertical reaction in every support in my model. So then I upload it, and it starts running through this model. It reads the Excel file. You can see it finds some errors. It says, oh, I couldn't actually find this sheet in the model that you said existed. So it automatically goes in and tries to find what sheets are there then. Ah, you spelled it wrong. It's actually this one here. So it goes through, finds its own mistakes, and keeps going until at the end, it says, okay, now you just tell me what load combination you want to see. So I write, okay, I want to plot vertical reaction for load combination number 35. It runs some more Python code, and it gives me this plot here, which is not very nice, but it's a pretty good starting point. So then I wrote one more prompt to say that I would like it rounded. I want to move these tags up a little bit, and I want circular points instead. And then you get this plot out here. This is after just 5 minutes, if not less, of fiddling with this. This here you can, of course, fine-tune to be much nicer. And I think the key thing here is that you can make it so it gives you a diagram for every single load combination. And then I asked it to then give me a Jupyter notebook, like the notebooks I just showed you. I don't want to have the code in here on the web browser. So I downloaded this file. You can see it here. So now you have a calculation template. You need to do some work to it, of course. You want to maybe change the explanations a little bit, explain how it's used. You definitely want to QA the code. You want to make 100% sure that it does what you expect it to do. But this is the code that it gave us. And then I see down here, try to run it. I get a mistake down here. I'm like, okay, I know why it does that. So I need to write this here. I could also ask it to fix this. But then we get the plot out that we just saw before. And I could ask it to loop through all load combinations, so we get all the plots out. And this you can also do for like column forces. You can do it for like basically any information you want to show on a plot. So this I was quite excited about. I was like, whoa, I remember doing a template for this in Excel some years ago. Really nice template, but it probably took me like 1.5 days to get it really nice. Then I programmed it in Python. It probably took half a day. And now programming it in Python with the help of AI takes a fraction of the time. But you need to know the code, and you need to be able to know what can be done with Python. The next one is an example which was kind of for me an eye-opener for what is possible with Python. So I worked on a tall tower where we had a core in this tower, like a concrete core. And my boss asked me, he was like very interested in how much of the moment that comes from the wind, how much goes into the core and how much is going elsewhere in the building. In ETABS, when you get the reactions out in a core, the internal forces in a core, you get them around this green axis, like the 2 main axes on the core, which makes perfect sense for core design. But I wanted to show it around any axis, and I just couldn't do that with ETABS itself. So I had to do some post-processing. And this is my first Python tool I've done with Python and using this big data stuff in Python. So it's not the cleanest code. This was also before any AI, so it's all handwritten. But basically, I wrote a little template where you can upload your output file from ETABS, and I tell the user what sheets it is I need here for it to work, then I do a lot of pre-processing of that data here. We don't want to go through that, but when you look at it, if you just look at one line at a time, it's quite simple stuff. I bet if you read through all of this, you would kind of know what's actually going on from reading it. Then where the fun part comes is down here. So one thing the program could then do is for every load combination, it could show me the displacement, like nice displacement curves. And I'll just have a folder with all these files. So I run my ETABS model, and then I get this folder with nice diagrams out for every load case. So we have the wind. We also can do the story drift, so the drift of every floor, which is also important when doing high-rise design. But the most important one is this one down here, where you can see just go down a little bit, that for every load case, I check the total moment we have in the building, and then I look at the pier force, like the internal forces of the core for that very direction. And you can kind of see something is going on here. Like I have a podium on the building. I think it was a podium here. And I can plot this for any wind direction. You can also get the shear forces. They come down here. They have a lot of diagrams because of a lot of load combinations. But here you see the shear diagram. I remember that we had an Excel template that could do the same thing. And it was so much copy pasting, and you had to be so careful. Here, when it's done, it works. You don't have to do any copy pasting. You just upload your Excel file and you're ready to go. So this is one of the most useful tools I think I have I've made for find element analysis post processing. The next example is one that is a little bit more complex, and I have only had a use for it once, but I want to show you what is possible with Python. So you can do finite element analysis inside Python. So as you can see, I'm taking a few notes from this from the course with here today. But this one here is an example where we look at a beam. So you have a beam here. And this, to keep things simple, we've just used a steel beam on springs. And it's a simple structural system, but it's not very simple because depending on the stiffness of the beam, you're going to have one distribution of forces. Then if the springs here are varying stiffness, you're going to have a different distribution. And I worked on a building. There's a ground slab we were designing, and we tried to really push it as far as we could in terms of material reduction. So we had to do some sensitivity analysis of floor stiffness and plate stiffness. And there, like, okay, we need to be able to run a lot of models, very simple models. So we used Python for that. So I'm not going to go through this code here because it will take it will take too long to explain to fit into this course here. I think what is important here is that you can create an FE model. Like here, what I actually do is I make a model that's an FE model, and I divide it into some segments. I add some nodes, like this extremely manual way of creating an FE model, which is why it's rarely something you would use for normal situations. But when you need to perform a calculation many times for a simple model, then it may make sense to do this. So it's a library. It's called, just to mention that, Pinite FEA. So we run a lot of finite element models. We do the analysis inside Python, and then we come down to the end here, and then we can start plotting the deflected shape under point load. So you can see when we press in the middle, kind of like bent down in the middle, the ends go up. So this is for what is it called, compression only springs. So the ends here can just lift up. If you have, and you have the reactions here. So you have the reactions only in the middle, as you may expect. But then where it gets really fun, this stuff here, is when we can start plotting them together. So here we are checking 5 different stiffnesses of beam. And then we look at the displacement, like how much is the displacement of this beam depending on the stiffness of the member. So we're running a lot of models, and we can see that obviously the stiffer it gets, the less it bends down. But probably more interesting is that it also activates a bigger area of the beam, which you can also see down here in the shear. For the very low stiffness, you only activate this area here. And as you increase the shear, you activate a bigger area. So on a project, what we used this for was to get an idea of how sensitive our system was. Like, what if our ground in reality is maybe 10% less stiff than we expected to? What impact will that have? And then with this kind of analysis here, we could very easily show that, hey, it's not very sensitive what we have here, so it's not a problem. If you have such cases, Hynide can really be extremely useful for that and take a fraction of the time compared to setting up 10 different FE models. So that brings us to the next example. I actually think this here, I can't remember if it's the last one or if I have one more, but this is a bigger program. So a lot of these programs you've seen here, like some of them are maybe like half an hour to an hour of programming once you know how to do it, and other ones are still like a day, if not more, of work. Like the one I showed you with the ETABS data was definitely a bit longer than just an hour or two. But here is a program I made when I had a bit of free time some months ago, where I've always been quite fascinated by vibration analysis. You have, again, I mentioned this book before, or the guide, a design guide for footfall-induced vibration of structures, which is a method that allows you to take an FE model and analyze all the modal shapes in every single point. And then from that, you can actually calculate the response factors. So I've seen how many engineering departments, what they do is that they have one model for the normal analysis, and then they use a different program, different model that they build over there for the vibration analysis. I thought with this method here, we can quite easily do vibration analysis on a modified version of the model we already have. We don't need to build a completely new one. So this is a slightly bigger program than the others, and I'll just go to the end output because that's the interesting part. And we have the source data. So the source data is again just an output file from cannot open the specified file. It's very, very similar to this file I showed you before from ETABS, just long table of information. So I go in here and I give some vibration input, like how heavy is the person walking? What is the damping of the system? What is my area type? What are the frequencies I want to check? What is the name of my Excel file with output from, in this case, safe? And then this is, of course, the programming work. I'm not going to go through this, but I translated the CCIP guide into code. So again, this turning a mathematical formula into code and doing some iterations over the data. And then we get down to the fun part, which are these plots here. So I've now taken the node in the model that had the worst response factor, and I can make a plot showing exactly at what frequency this happens. So I can see it's a bit about 2.1 hertz. We get this peak, and I can see what is it called? What number eigenfrequency it hits at. So we combine the 4 eigenfrequency curves and get this sum to get the full response factor. And now that I've done it once, I can take any safe model and run through this. And you can also create a plot like this one here, if we zoom out a little bit. So you have the full FE model here, shown in plan, and it automatically marks that here you have a max response factor of 8.5, and also shows all the other nodes, what response factor you have there. You can also show the eigen modes here, the modal shapes. So I think this here is definitely not a clean tool. It's one I really want to clean it up and make it nice and user-friendly and put some explanations into what things are doing. Like you would go up here and you would start explaining here. So in the next piece of code, we do blah, blah, blah. So someone who reads this code can actually really understand what's going on. That's a good template. So that's the next step to this program I'm writing here. So this is a bigger script. This has taken me many hours to work out and QA and get to work. But that's where you can take it to if you really want to make something a bit bigger. Then I just want to mention here at the end that I am making a course, Python for Structural Engineers, where you can learn this. There's a web page that will hopefully launch very soon, and the course is going to come out later this year. And yeah, it's just a lot of small videos taking you through notebooks with exercise and small quizzes, and very much focused on like the pragmatic use case. So not you have to become a programmer, but how can you solve everyday tasks with Python? So the things you saw today can maybe seem a bit maybe intimidating, but as soon as you know the basics of Python, you can use ChatGPT also to get an explanation of some of the code. You can generate code. So I think it's easier than ever to learn Python. If you want, you can go into this web page and sign up to be notified. So yeah, pythonforstructuralengineers.com. And I think that was what I wanted to share with you today.
Great.
Stop sharing here.
Thank you very much for this brilliant presentation. It's been great to learn so much about how we structural engineers can use Python. I'm sure there are questions in the chat, so let's start a Q&A session, and we'll pass it on to Etienne and Jan, who will read out the questions in the chat. If you still have some questions, please drop them in the chat and we'll address them now. The first question we have is from Abri, and it's the question about your course. When will you release your course?
My time plan right now, I'm aiming for October, and we go crazy production mode right now. So that's the goal, is October.
All right, the second question would be from Philip, but I think it's kind of answered in the chat, but maybe we can get your comment on it as well. In Jupyter notebooks, are you able to use values returned in Python code in the markdown cells?
Okay, can you say that again? Sorry.
In Jupyter notebooks, are you able to use values returned in Python code in the markdown cells?
That's a very good question. Not by using it in a normal way. I don't think you can. Actually, I have never even considered that. I don't think you can. I would be surprised if you can, but you may be able to find a workaround.
Okay. Any other questions you could write in the chat? But there's another question. What do you want to say on using Grasshopper in place of Python, especially for geometry of model? So
it's a very, very good question. And I am myself a Grasshopper, I'm a Grasshopper nerd. I love Grasshopper. But I think Grasshopper and Python have two sometimes overlapping use cases, but also a lot of non-overlapping use cases. When it comes to geometry processing, like making geometry where you actually want to work in a 3D space, Grasshopper is the way to go. If you work with data, you can sometimes use Grasshopper for some visualizations there, but I would actually say that's more of a Python task. So anything that has to do with reports, data processing, text file editing, all these examples I showed you today, those make sense to do in Python. Geometry, complex geometry, or they say even links to other softwares is often easier to do in in Grasshopper because there are a lot of great plugins in Grasshopper. The reason that I've decided to focus more on Python now is my experience has been that I've had a lot of success with developing small little tools in Python in my work that has been adapted by others. So I've spent very little amount of time to create a tool that other people then started using in these like small little daily tasks. I think, hey, okay, I think Python has a more pragmatic everyday use case, and Grasshopper is something that you can just work a lot better with geometry with, and a lot more. Like both are worth learning, but you can also use your Python knowledge in Grasshopper because you can write in Python inside Grasshopper.
Okay, thank you. Another question will be, have you ever used the library handcalcs to render structural calculations?
Yes, handcalc is awesome. There's handcalcs is really good. So there are some packages that are very good for structural engineering. It's so you can use, there's a package where you can use units. There's also another structural engineering library, I think called section properties, where you can calculate section properties. And handcalc is a library that just makes it easy to make real looking reports and really render your handcalcs. So definitely a package. If you learn Python, it's definitely worth learning to use this package. And as like when you know Python, it takes no time to learn that.
Also regarding the libraries, what Python library did you use for your Python FEA example of beam spring modeling?
So for that, I used I can't remember all, like, but it was based on something called PyNite FEA. So Pi, like in Python, and then NITE. And I believe it's actually open source. Yes, I think it's all open source, and there's really good documentation online, lots of examples. So it can be a little bit tricky to do like this because you can't see the geometry while you're modeling, and it can be a little bit tricky to use, I will admit, but when you have the right use case for it, it's extremely powerful.
There is another question of, can we use AdSec and Python and how they can relate?
Can we use what, sorry?
AdSec, I'm not sure if I'm saying it ADSEC. Do you know about that, AdSec?
No, that is
Oasis
AdSec.
AdSec, yeah.
I don't know. That depends. So I can't answer that.
Maybe Jan, you want to read?
But I just want to say,
Yeah.
if you can export, so there are two ways of using Python with software. One is through what's called the API, where you talk directly with the software. So you have like this dynamic link back and forth. Maybe not, you can do that. But if you can use a text file as input to the program and it can spit out CSV or Excel files in the other end, then you can pre-process the input and you can post-process the output. And I think you can do that for any package.
Okay, thank you. Another question, what's your approach for QAing your codes and checking that it does what you want it to do?
So this is actually a very, very good question, because if you are a full-scale programmer, like if you're developing software, the way you QA your code is probably different from the way I QA my code, because there you have to make sure that even if the computer explodes, your function still does not return something unexpected. The way I QA is first to actually read my code to make sure I haven't made any mistakes. I'm asking ChatGPT if the mathematical formula I'm maybe translating corresponds to my code. Those are the quick checks. And then I do maybe like all sorts of hand calculations on the side. I know this should be this, this should be this, this should be this. And if my code returns those values, then I know that part works. But one thing to add there is that when you build a big tool, you can't just write everything and then QA at the end. You QA the modules. So you write one little function and you're 100% sure that that gives you the right result. So you do that for every module. And then when you stitch the modules together, then you do some hand calcs to check that, hey, the stitched together modules also together give you the result that you expect. So hand calcs, pen and paper, or Excel on the side. That's the way forward.
Another question, is it possible to add any Python packages inside Grasshopper like Pinite and FE?
Yes, I'm happy you asked, because this is something that I have been frustrated about for years, that it was not possible. But now in Rhino 8, there you have in Grasshopper there is a new Python component where you can use all these packages here. Something like Pinite is probably something I would not necessarily use in Grasshopper because they're great FE packages there already. But Pandas, for example, was this Excel library. I've used that. Matplotlib is amazing because you can generate these beautiful plots. And I've also used some like graph networks. So if you want to do some graph analysis and especially iterative things, it's really, really useful with the Rhino 8. So I was a very happy man when Rhino 8 came out.
Okay, thank you. And another question is, can we use the Python programming language with Mathcat? Do you have any experience with this?
I would say as a basis, I haven't used Mathcat like for a long time, and I'm not actually sure whether there's a direct link between the two. But one thing that is quite interesting is that from this plotting library is like Matplotlib. One way of using that is basically a mirror image of how you use Mathcat. So it's very, very similar in syntax and the way you do things. So if you know Mathcat already, the jump is very easy. I haven't tried doing a mix where you mix them together and use them. I'm not sure if that is possible and whether it would be smooth or not.
There seems to be a lot of questions about integration of two software.
Yeah.
So one of them is Python and Sophistic. How can it ease work of modeling?
So I think when it comes to integration, maybe to take it on a bigger level. If your FE software can have these input files, I know Sophistic, for example, has its own programming language, Teddy, where you can make your FE models. There you can edit those files with Python and it will work really, really smoothly. I know as far as I'm concerned, I also think that Sophistic has a pretty good API. I haven't touched it with Python. I've used it through Grasshopper before. But I believe it should be possible to do direct integration as well if you wanted to. One thing to be mindful about when we talk integration, I think our biggest responsibility when we make tools for ourselves and for our colleagues is that they're transparent. I think we engineers, we generally have a mistrust, which is very good. I don't trust a black box. If you give me a file and you say, when you touch this button here, your model will automatically update. It will automatically update all your spring stiffnesses and you won't even have to do anything. I just won't trust it. I want to see exactly what is being changed. And I want to see it in such a raw format that there is no doubt for me that anything else has been changed. As soon as we start making the black boxes, we introduce, like, worst thing is we introduce bugs and no one ever discovers it. The next worst thing is that the users won't trust it and just not use it. So I think the best tools you can make are the ones that are the most transparent, which is why I know how to use ETABS directly with Python, like push data in and change stuff in the model. But out of principle, the only time I do these direct links is to extract data out. Because I know if I extract data out, I can kind of check it. But if I push data in, it just scares me. I don't want to do it.
Okay, and the last question we've got in the chat is, would you recommend Python over C#? If yes, why?
Yes and no. If you sit with a developer dream inside you, and you actually want to become more of a plugin developer, a software developer, I would say go C#. Also, if you maybe think, okay, the learning, like you can take a steeper learning curve, I would say C# can also be good. The downside to C# is that you don't have this notebook format. You work all the time in like these code files. So the templates you're going to be making for other are not going to be as easy to use. It's going to be like little programs, where what you can do with Python are these notebooks. I think the notebooks are more transparent. So if you just want to be a better engineer, Python. If you want to do more development, go with C#.
Well, I know Jan said it's the last question, but there's another question. Which source would be the best to install Python on computer? I think we should say this is the last, being conscious of the time. So
what source I would recommend anyone that starts learning, like start with Google Colab. Like there's no need to start worrying about setting it up on your machine when you start learning. There Google Colab can really take you a long way, and it's just like it works out of the box. I have personally used, when I installed on my own computer, I've tried it in two different ways. One is through something called Anaconda, where you basically just download an installer, you run it, and it works. I've also done more manual installations of everything, which also works fine. Depends on company policy. I think that's also a big thing. Companies have different policies, and it could be that one way is easier to install in your company than the other. But definitely Google Colab is, well, you already have Google Chrome installed or at Microsoft Edge, and there you can run it. So you get around all the like IT safety measures.